Welcome to True Projects. In this video, we are going to explain about the project title Video-Based Vehicle Speed Estimation using Speed Measurement Metrics. Before diving into the execution, let me give you an overview of the project. Video-based vehicle speed estimation involves analyzing video footage from cameras to determine vehicle speeds. This method utilizes object detection, tracking, and motion analysis techniques to calculate vehicle velocities in real time. Traditional methods like optical flow, feature tracking, and background subtraction have limitations such as sensitivity to noise and lighting changes, making them less effective in crowded scenes and occulted environments. The proposed system integrates deep learning based object detection algorithms such as YOLO V5S, YOLO V5X6, YOLO V3, YOLO V8N, and YOLO V8S with speed measurement metrics for more accurate and real time speed estimation. Video based vehicle speed estimation is essential for enhancing road safety, traffic management, and infrastructure planning. By accurately estimating vehicle speeds from video footage using computer vision and deep learning techniques, the project enables real time monitoring of speed limits, leading to safer roads and more efficient traffic flow. Performance evaluation involves assessing precision, recall, and MAP, mean average precision, to gauge the system's effectiveness. This project can benefit transportation authorities, law enforcement, engineers, researchers, manufacturers, and the public by enhancing traffic management, safety measures, and overall road efficiency through improved speed enforcement and traffic analysis capabilities. To implement this project, we need software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Algorithms used. These are the algorithms built in the project for vehicle speed estimation. We have built these YOLO models to compare the performance with different evaluation metrics like precision, recall, and mean average precision MAP score. So here in this project, we have used the YOLO models, different versions of YOLO models for the vehicle speed estimation. So let me explain you in general what YOLO models are. YOLO, which stands for You Only Look Once, is a state-of-the-art object detection algorithm that processes images in real time, providing a fast and efficient method for identifying objects within them. It operates by dividing the input image into a grid and predicting bounding boxes and class probabilities directly from this grid. Unlike traditional object detection methods that require multiple passes over an image, YOLO performs detection in a single pass, directly predicting bounding boxes and class probabilities for multiple objects simultaneously. This approach makes YOLO, You Only Look Once, particularly well suited for applications requiring real time processing. Although all versions have similar objectives, they differ in their architectures. Now let us execute the project. To execute this project, first we need to open the code folder which contains the project source code files. So here this is a sample folder in which we have the test cases which we will use during the execution. And here this is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, home.html, about.html, and more, which represent different pages of the website. And here these are the datasets folder. So in this folder, the dataset is split into training and validation. In the training folder, again, we are having two folders, namely images folder and the labels folder. In the images folder, we have the images of the vehicles for which we will detect the vehicle speed. And all these images are used to train the YOLO V5 model. And in the labels folder, we will have labels or annotations for objects in the corresponding images. So each label file corresponds to an image file in the images folder, providing details about the object's locations and classes within the image. These label files often follow the YOLO format, where each line represents a detected object. Each line specifies the object's class index, followed by its bounding box coordinates normalized to the image dimensions. So here, let me open the first label. So here, in the first image, three vehicles are detected, and here we are having the annotations for those three objects. So here the first one is the class index, and the four are the coordinates of the bounding box. So we will detect the object using the bounding box, and these are the coordinates of the bounding box. So here, this is the label for the image, this. So all these images are used to train the YOLO V5 model. And similarly, in the validation folder, again, we are having the images folder as well as the labels folder. In the images folder, we have the images of the vehicles for which we will detect the vehicle speed. And all these images are used to evaluate the performance of the YOLO V5 model. And in the labels folder, we have the annotations or labels for the images present in the images folder. And here, this is the vehicle speed detection YOLO V8 dataset. So again, this dataset is split into training and validation. So in both training and validation, we have the images folder as well as the labels folder. And in the images folder, we have the images of the vehicles for which we will detect the vehicle speed. And in the labels folder, we have the labels for the images which are present in the images folder. So the images which are present in the train folder are used to train the YOLO V8 model, and the images present in the validation folder are used to evaluate the performance of the YOLO V8 model. So here, this is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. Here, I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. So here this is the code folder's path. Compile the app.py file using the command python space app.py. So here I am typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered, so click on login. So here we need to enter the username and the password, which are static, and then click on login. We have logged in successfully and we are redirected to the prediction page. So here we need to upload the images of the vehicles, and after uploading the images, the application will detect the speed of the vehicle. So click on choose file to select the images. So here from the test cases folder, I'm selecting the third image. Now click on open. So here we can see that the image is loaded. Now click on upload button. So this is the image which we have uploaded, and here we can see that the application has detected the vehicles with the bounding boxes, and on top of the bounding box we can see the name of the vehicle along with the speed of the vehicle and the probability score. So here we can see that the cars are detected with the blue color bounding boxes, and on top of the bounding box we can see it is written as car, and here we can see the speed which is 60, and we even have a probability score which tells us the confidence level of the application in labeling car speed has 60. So here we can see many cars are detected with their speeds and probability scores. Now let us upload some more images. Click on detection link here. Click on choose file. So here I'm selecting this image. Now click on upload button. So here we can see that the vehicles are detected with the bounding boxes. So here we can see a truck is detected with a green color bounding box, and on top of the bounding box we can see it is written as truck and the speed of the truck is 40. And here we have the probability score which tells us the confidence level of the application in labeling truck speed has 40. And here we can see some cars are also detected and the speed of the cars is 60 for each car, and we have the probability scores here. Let us upload some more images. Click on detection link. Now let us upload the images from the train dataset itself. So here from the dataset, from the YOLO V5 dataset, from the train folder, I'm selecting this image. Now click on upload button. So here, this is the uploaded image, and here we can see that the vehicles are detected with the blue color bounding box. And on top of the bounding box, we can see the name of the vehicle and the speed of the vehicle. So here, this is the vehicle which is detected, which is a car. And here we can see the speed of the car, which is 60 kilometers per hour. And here we have the probability score, which tells us the confidence level of the application in labeling car speed as 60. So here we can see many cars are detected with the 60 speed. Now let us upload some more images. Click on detection link. So again from the train dataset, I am selecting this image. Now click on upload button. So this is the uploaded image, and here we can see that the vehicles are detected with the bounding boxes. So here we can see a truck is detected with a green color bounding box, and on top of the bounding box we can see it is labeled as truck along with the speed which is 40 kilometers per hour. And here we have the probability score, and many cars are also detected, and we can see the speed of the car which is 45, 45, 45, 45 along with the probability score. Let us upload some more images. Click on detection link. Now click on choose file. Now let us upload the images from the validation folder. So here I am selecting this image. Now click on upload button. So here this is the uploaded image, and we can see that the vehicles are detected with the blue color bounding boxes, and on top of the bounding box we can see it is detected as car, and the speed of the car is 90 to 120 kilometers per hour. And here we can see the probability score, which tells us the confidence level of the application in labeling car speed as 90 to 120. Now let us upload some more images. Click on detection link here. Click on choose file. So I'm selecting this image. Click on upload button. So here we can see this is the uploaded image, and the cars are detected with the bounding boxes, and on top of the bounding box we can see the name of the vehicle, which is car, and here we have the speed of the vehicle, which is 90 to 120 kilometers per hour, and we even have the probability score. So we can see three cars are detected in this image, and the speed of the cars is 90 to 120, 90 to 120, and 60 kilometers per hour. And we have the probability scores, which tells us the confidence level of the application in labeling car speed has 90 to 120, 90 to 120, and 60. Let us upload one more image. Click on detection link. Now click on choose file. Let us upload the image from the YOLO V8 dataset from the train folder. So this time I'm selecting this image. Now click on open. Now click on upload button. This is the uploaded image, and here we can see that the vehicles are detected with the bounding boxes. So here this vehicle is detected with a blue color bounding box, and on top of the bounding box we can see the name of the vehicle, which is a car, and the speed of the car is 45 kilometers per hour, and here this is the probability score. So in this image many cars are detected with the speed has 45 and the probability score. In this way, just by uploading the vehicle images, we can detect the vehicle and the speed of the vehicle along with the probability score. Now click on graph link here. So here, this is the precision and recall graph of YOLO. On the x-axis, we have the recall score, and on the y-axis, we have precision score. And this is the F1 score graph of YOLO, F1 confidence curve. And this is the confusion matrix of YOLO. And here we have the precision comparison graph. Here on the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a measure of the correctness of positive predictions made by a classifier. And this is recall comparison graph. Here on the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall is a measure of the classifier's ability to correctly identify all relevant instances from a dataset. And this is the MAP comparison graph. On the x-axis, we have the MAP score, and on the y-axis, we have algorithm's name. MAP is a metric for evaluating performance of algorithm in tasks like object detection. It calculates the average precision for each class and averages these values across all classes, providing a comprehensive measure of model performance. So the algorithm which is performing best will be used for prediction. In conclusion, the project has developed a video-based system for accurately estimating vehicle speeds, offering cost-effective and robust solutions for traffic monitoring. This technology presents significant benefits for improving road safety, optimizing traffic flow, and enhancing transportation efficiency. Now click on sign out.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.